I've written the matrix that we obtained previously here. Remember, this matrix equation tests whether these three columns are linearly independent. If it's possible to solve this matrix equation with anything but C1 equals C2 equals C3 equals 0, in other words, if this column is anything but the 0 column, if the solution consists of anything but the 0 column, then these three columns would be linearly independent. Okay, by the test for linear independence. Okay, well, people wanted to tell me then that to test this, you could write down the augmented matrix and reduce it. Well, under what circumstances then would you have a non-trivial solution? And under what circumstances would you have only the trivial solution? Well, the matrix is going to reduce, okay? And the matrix you get, well, the augmented matrix would just be these three columns and then the 0 column, right? So you'd have a matrix with three columns and then a fourth column consisting all of zeros. Now, you know, these three columns would originally be these three, but it could be that this matrix reduces down to the identity, okay? Whatever the augmented matrix reduces down to, it starts with a column of zeros. The fourth column will be a column of zeros, and there's no valid row reduction operation that would change that. Whatever multiple of whatever row you add to whatever other row, you're still going to have nothing but zeros over here. Whatever you multiply a row by, well, if you multiply 0 by 0, you get 0, so you're still going to have 0 here. And if you switch two rows that have zeros in the fourth column, you're still going to have zeros in the, nothing but zeros in the fourth column. Okay, so the point is now, this matrix will reduce. We didn't actually reduce it, we're just looking at conditions and possibilities. Okay, so anything could happen with this matrix. It could be that this matrix reduces to the identity, in which case your augmented matrix would reduce to this, which would tell you, remember that the variables in this matrix are C1, C2, or the variables, excuse me, in the equations that this matrix equation represents, the system of three equations, the variables are C1, C2, and C3. Okay? If this is x, y, z, the variables will be x, y, z. If it was x1, x2, x3, the variables would be x1, x2, x3. So in that context, you understand that this stands for the matrix equation C1 equals 0, C2 equals 0, C3 equals 0. If you write out the corresponding equations in C1, C2, and C3, that's what it's going to tell you, so that all the three constants, C1, C2, and C3, have to be 0. Thus, you've satisfied the test for linear independence. And no vector can be a linear combination of any of the others. Okay, well, we discussed, but I never wrote out, the other possibilities. So let me just kind of write out. Another possibility is just looking for a different color of chalk to distinguish this from everything else. Okay. If the reduced matrix is this, okay? Or even if you have some non-zero number here and here, you're still going to have zeros over here, as we said before. You can't combine a matrix with a column of where the fourth column is all zeros. You can't combine the rows in such a way that you get anything but zeros in the fourth column. So what does this say? This says that C1, well, this says that C3 is a free variable. So you could let C3 equals T, and then this equation says C2 plus whatever multiple of T equals 0. And this star just stands for some number, not multiplication. And also C1 plus some other number is equal to 0. Now, I'm not going into a lot of detail, but these could be any two numbers, so you could have any two numbers here, depending on what you get when you reduce the matrix. Whatever you get when you reduce the matrix is the number you're going to get here and here, will go here and here. Well, here and here, put them in the right order. And that's the equation of a line. Those are parametric equations for a straight line through the origin. Okay? And what I just said about parametric equations for a straight line through the origin, that comes out of it, but those are not the parametric equations. Okay, that was just slipped a couple steps ahead, and those are steps we're not going to take. We're not going to bother with those steps. The point is then that this is valid for any value of T. So you have, T doesn't have to be 0. If T isn't 0, then C3 isn't 0. And it turns out that neither is C2 or C1, unless you happen to have zeros here. But the point is that C3 is non-zero, so this gives you a non-trivial solution, so it's not linearly independent. So if this matrix reduces down to something other than the identity, you're going to have at least one free variable. Okay, you could have two. You could have a row of zeros here too. Okay, but what the matrix reduces to determines whether you have a linearly independent set or not. It also determines how many free variables you have, so you know what kind of subspace you get. And when I said this gives you a line, this looks something like the equation for a line, I was wrong about that too. This would give you a plane in this situation. And that's something I know perfectly well. But I misstated it, okay? The point is, though, that you don't get linear independence. If it reduces to this, it's not linearly independent. If you have one or more rows of zeros, your vectors, your columns of your original matrix are not linearly independent.